Okay, if everyone could mute their microphones, please, and we'll begin. So good afternoon, folks. Thank you for tuning in to another Risk Institute online session. Today, we're really fortunate to have with us the wonderful Mr. Enrique Miralles Dolz, our very own, who will be talking to us about his research on interval-based global sensitivity analysis for epistemic uncertainty. The presentation will be around 45 minutes with around 15 to 20 minutes for Q&A. But please make sure that your mics are muted. And if you'd like to leave any questions in the chat or raise your hand afterwards, we can take questions. So before we begin, I'd just like to make a few quick announcements. So we have a few talks coming up. Excuse me. Dr. Dalal Arajer on the 6th of June at 12 p.m. So next week. Then following that, we have Dr. Sylvia Tolo on the 14th of June at 2 p.m. our alumni. On the 21st of June at 2 p.m. we have Dr. Dominic Balog-Way, who will be talking to us about the evolving field of risk communication. Where are we now and where are we going? And then on the 19th of July at 2 p.m. we have David Ropik talking about the overlap of risk communication facts and feelings. So let me introduce our speaker for today's talk. So Mr. Enrique Miralles Dolz joined the Institute for Risk Uncertainty in 2018 for his doctoral studies, working on uncertainty quantification, sensitivity analysis, and optimization under uncertainty, primarily in systems under epistemic uncertainty. Before that, he studied engineering in Valencia, Spain, and physics at the York Plasma Institute. In his free time, he enjoys reading about history and philosophy of science, lifting weights, and going for a walk. So welcome, Enrique, and everyone here. And let's start sharing your slides, Enrique.
Yeah, sure. Can you see it? All right.
Yeah, fantastic.
So thank you, Francis. So I will start basically explaining or defining sensitivity analysis. So according to Saltelli et al., so it is the study of how uncertainty in the output of a model can be apportioned to different sources of uncertainty in the model input. So basically we have a mathematical model which takes some inputs and gives an output or outputs. And we want to understand how the uncertainty in the input affects the uncertainty in the output. So why should sensitivity analysis be required? This is a funny quote. It says, sensitivity analysis for modelers. Would you go to an orthopedist who didn't use X-ray? So basically, mathematical models are used almost everywhere. When we design cars, we have this computational model. We try to find what is the best shape of the car or the best engine for the car. And then we want to test also some hypotheses. We put this car in the wind tunnel and we want to check whether it behaves like we predicted with our model. Mathematical models are used also to calculate costs. We expect some revenue from a specific model, and we try to calculate when we are going to release this car, the model of the car, because if we release it, I don't know, maybe in summer, it maximizes our revenue. However, uncertainties are also almost everywhere. When we move from the computational model to the physical model, then in that process, there are some inaccuracies because the machines are not, there are some inaccuracies in the shape of the car, for example, or the painting, or the power that was predicted for the engine. Also, experiments in the wind tunnel are subject to measurement errors, depends on where you put the different diagnostic systems. And also the diagnostic system itself is dependent, it has some measurement errors. And costs in the future, if you are predicting how the revenue you're going to make in the future, these costs are subject to unexpected events as well. There are things that you simply cannot predict. So what is sensitivity analysis useful for? So first and foremost, to understand the model under investigation. So if we're going to make some choices, some decisions, depending or according to the model, then we should understand the consequences of our assumptions. Also, sensitivity analysis can be used for research prioritization. So it can tell you whether can tell you what region of the model should be inspected further, where you should invest the most. Um, and also it's useful for model reduction. If you have a computational model that it's very computationally expensive, it takes a lot of time to run, um, then maybe you want to reduce it, and you want to reduce it where it is not going to affect the accuracy too much. Um, so what are the sensitivity analysis approaches? So according to Rasavi et al., they made this classification. So there are derivative-based approaches. These approaches are kind of the best known approaches. They started in physics, and they basically compute the derivative either analytically or numerically, and they measure the change in the output when the input is perturbed around a range. Distribution-based approaches like Sobel indices, they decompose, in the case of Sobel, they decompose the output variance and assigns it to the input variance. So how much of the output variance can be apportioned to the input variance. Regression-based approaches like the coefficients of a linear regression, correlation coefficients, and other machine learning approaches. And there are other approaches that are usually a combination of all of this. So what are the limitations? In the case of derivative-based methods, we need to know the analytical function, the analytical description of the function. Also, we have to define a base point where we are going to perform the derivative. And also, we have to define a perturbation size for that input parameter. In the case of distribution-based, the output distribution is dependent on the input distribution, and this input distribution is not always known. And in the case of regression-based, we make some prior assumptions about the model, how it behaves, if it's linear, polynomial, concavity, etc. And also the quality of fit can introduce further inaccuracy. Well, yeah, so this is kind of the elephant in the room, aleatory versus epistemic, or variability versus imprecision. In principle, probability theory can describe both. That's what some say. But the fact that is that probability theory conflates observed data and subjective belief. It doesn't make a distinction. And this difference is essential when we are assessing models. Imprecise probabilities attempt to separate them, attempt to combine different methods to describe this variability and imprecision, like probability bounds analysis or the Dempster-Shafer evidence theory, infogap, etc., etc. So epistemic uncertainty in engineering, it's ubiquitous in engineering, epistemic uncertainty. There's this called the aspiration of a digital twin is a close one-to-one mapping between a physical and a virtual system. Well, we can start thinking about the challenges that this enterprise brings, right? Moving from a virtual system to a physical one and vice versa. In fact, when we are designing engineering systems, we're often concerned about the future. We wanted to solve some problem, and we want to imagine some system that doesn't exist, like a nuclear fusion power plant or a Martian base. And there are a lot of uncertainties around that system. Also, computational models cannot perfectly capture reality. Reality is simplified, otherwise the model would be intractable. And therefore, the verification of such computational models without reliance on subjectivity is therefore of paramount importance. In the case of policymaking, according to the better regulation guidelines of the European Commission, they say not all sources are equally robust, and one should consider when and how the evidence was collected and whether it is subject to bias or uncertainty. So we are kind of in the age of evidence-based policymaking. We have a recent example with COVID and the SAGE, the Scientific Advisory Group for Emergencies. They basically employed models to guide policymaking. And these models are inevitably under epistemic uncertainty. If something is unknown, it must be acknowledged. If something is assumed, it must be acknowledged. Conflating variability and imprecision is not a transparent move. So in general, mathematical models used for engineering, science, economics, policymaking, the analytical description of model functions is not always available because we are dealing with black box models, because these models are very big, they have many different dependencies, and it's difficult to disentangle the different functions. There isn't consensus about the base points or perturbation size of the input parameters. We make unsound assumptions about their input distribution functions, or we simply don't know the model behavior. If it's nonlinear, if it's non-monotonic, simply we don't know. So issues 1 and 2 clash with derivative-based approaches. Issue 2 clashes with distribution-based approaches, and issue 3 clashes with regression-based approaches. So interval analysis can help with this. Interval analysis basically attempts to measure output bounds of a model. It makes no assumptions about the input uncertainty other than its existence between two bounds. It is a suitable alternative to describe epistemic uncertainty because we are not making any assumption about the mass inside that interval. And it can be performed with interval arithmetic, sampling, and also optimization. However, we haven't explored this approach for sensitivity analysis. The idea comes from this example. In this paper, Helton and Davis say the simplest sensitivity analysis procedure is an examination of the scatter plots associated with individual sample variables and the particular model prediction under consideration. So we can see that in this example here, x1 seems to be a better predictor of y than x2. If we pick any value of x1, we can see that the interval of y is much narrower than in the case of x2. So we want to transform this qualitative intuition into a measurement. So we can do that with interval analysis. We can define a number of subintervals. We can divide this the domain of this input in n subintervals, and then we can measure the output interval, and we can compute this area shaded in red, and we can compute the area shaded in gray, which is the absolute the maximum output and the minimum output and the maximum of the upper bound of the input interval and the lower bound of the input interval. Then we can compute this sensitivity index. If the red area equals to the gray area, basically this index is 0, and we cannot predict y from xi. If the red area is 0, it means that y is completely determined by xi. So we can do this with interval arithmetic if we have access to the function. It is more rigorous because it provides an outer approximation rather than an inner approximation. And when we are dealing with safety and uncertainty quantification, it's better to have an outer approximation. It's better to be safe than sorry. And we can see the values of the sensitivity index here. The model says that, the method, says that x1 is more important than x2. We can see a small difference in the values because interval, as I said, interval arithmetic is more rigorous and therefore gives a more precise values. We could get the same numbers with sampling if we increase the number of samples, if the number of subintervals are the same. And these results make sense because, well, in this function, actually, x2 is not playing a role at all. And we also can see that y is not completely determined by x1 because there must be some other parameter that is maybe creating some noise, which there is. There's this Gaussian distribution here. So this method seems to be working here. Also, the interval-based method provides the information of all the information possible of the pinching for the given number of subintervals. A pinching is consists in reducing the input uncertainty from the interval to a point value, and then measuring how much the uncertainty reduction is. The problem of pinching is that you have to define a point for that reduction to perform that reduction in the input. In the case of interval based, you can simply reuse the data you used to get the sensitivity indices, and you can get the results of pinching for the entire domain. We can see that pinching x1 at 0 is the optimal choice for output uncertainty reduction, and x2 basically doesn't make any reduction in the uncertainty. So basically, the analytical description of model functions is not always available. We don't really need the analytical description because we can perform this with sampling. There isn't consensus about base points or perturbation size. We don't need to define any base point or perturbation size with interval based. And sound assumptions about input distributions, we don't have to make any assumption about the input distribution. There are not distributions at all. We have just to assume the interval of the input. And unknown model behavior, it doesn't really matter if the model is nonlinear, non-monotonic. It does, but it's the model doesn't depend on it. And as an extra, it provides useful information for model calibration and decision making with the pinching data. So 17 minutes, okay. This is an application using the Ishigami function. This is a well-known function in the sensitivity analysis and uncertainty quantification community because it's non-linearity and it's a combination effects between x3 and x1. And we are going to run an experiment with 3 scenarios. In the first scenario, the inputs will follow a uniform distribution between minus pi and pi. This is kind of the standard Ishigami function. In the second scenario, the inputs will follow a triangular distribution with a mode in 0. And in the third scenario, we are going to use the interval-based sensitivity analysis. So 1 and 2 will be analyzed with Sobel indices, and 3 will be analyzed with intervals. And so these are the results of the indices. We can see that for the interval-based, the most important parameter is x3, and the second most important parameter is x1. For Sobel indices, in the uniform case, the most important parameter is x1, and the second most important parameter is x2. And in the triangular distribution, the most important parameter is x2, followed by x1. And these are the areas used to compute the interval-based sensitivity index. So we can see that there is some discrepancy when we use different input distributions in the Sobel indices. These are the results for pinching. So if we can reduce the input uncertainty to a point value, then the optimal choice is reducing x1 to minus pi, 0, or pi. If reducing this to a point value is too restrictive, the second best option is reducing x3 from minus pi to minus 1, 1. And x2 returns negligible reductions in output uncertainty. So basically, it doesn't. There is no benefit in reducing x2. You can do a similar analysis using variance-based methods. However, in variance-based methods, the output uncertainty reduction is an average reduction of its variance when the variance of certain input is reduced some percentage. So I find this quite puzzling compared to the interval case. So in conclusion, interval-based sensitivity analysis requires only assuming the bounds of the input variables. This can be performed either with interval arithmetic, if you have access to the functions, or with sampling. variance-based sensitivity analysis like Sobel indices can return contradictory results under epistemic uncertainty. We just saw that if we assume one distribution or another, the ranking is different. Intervals may be easier to interpret than variances, especially for engineers. Engineers, we use to work with intervals more than with variances. But Sobel indices provide useful information about interaction effects. We haven't explored this with the interval-based sensitivity analysis. But yeah, this is something good of Sobel indices that at the moment we cannot do with interval-based, and I'm not sure we will ever do. And we have to remember that sensitivity analysis methods are diagnostic tools. We are diagnosing the model, and sometimes one method is not enough, and sometimes it is. Yeah, so I was quicker than expected, so that's it.
All right, thank you very much, Enrique. Wonderful presentation. Do we have any questions from the audience? I see Adolphus has already got his hand raised. Would you like to unmute yourself, Adolphus?
Can I stop sharing the screen, or it's okay?
Yeah, you can. No problem.
Thank you so much, Francis. Enrique, sorry, keep your screen because I have one question, a very short one regarding one of the slides.
Yeah, sure.
If you go to the table where you compare the results of the different from the different sensitivity methods, may I just clarify with you what does a total column mean? Is it the area or the some other matrix?
Say it again, sorry.
The total column. May I know what?
Oh, this is the total sensitivity index of Sobel indices. So Sobel indices calculate the first order indices and the total, which take into account the combination effects.
Mm-hmm.
So for instance, you can see that for x2, the total remain the same. However, for x1 and x3, the total are different. And this is because there are some combination effects between x1 and x3.
And by combination effect, you're talking about correlation?
No, I'm talking that in the function,
okay.
Some variance that depends on both things at the same time.
Right. Okay, sorry, my bad.
So interval based doesn't provide that information, but Sobel indices do, which is useful because you want to diagnose the model. You want to know whether there are some combination effects or not.
Right. Nice one. Yeah, thank you so much, Enrique. That clarifies it all.
Yeah.
Thank you, Adolphus. How about you, Alex? Would you like to ask your question?
Yeah, sticking on a similar thing, the distinction in the comparison between propagating uniform triangular distributions and then the interval, assuming you don't know the distribution, you just know it's bounded between negative pi and positive pi. Like what's the interpretation of that? Because looking at that, it's possible in the triangular distribution for the index of S2 to be 0.591, but that distribution isn't being considered under the interval. So the interval, it's what would you say is the interpretation if it's not like a propagation of different possible distributions?
Yeah, so what we wanted to do here is to show that for Sobel indices, the distribution you use for the input parameters does matter, and in some scenarios you cannot assume that input distribution because you simply do not know. For the second question, what is the interpretation of the interval-based index? It is how good that variable is predicting the output. I think that's the correct interpretation. I'm not sure I'm making sense. Is that
yeah. I think basically it was just, I don't know. In my head, I was wondering whether it made sense having the precise output value for an interval input if it's possible that that interval input could take an arbitrary number of different distributions, some of which give higher sensitivity indices through Sobel analysis. But I don't know if that's just a distinction between Sobel analysis and this method. I don't know. Yeah, I don't know if that makes I don't know if that makes any sense either, to be honest. But
so yeah, we just wanted to show that variance-based methods depend on the variance, and the variance, it's a probabilistic. It comes from a density, and it comes from a probability, a density function, and sometimes you cannot assume that it has consequences, and the consequences of assuming that, in this case for the Ishigami, the consequences of assuming uniform, well, assuming uniform has consequences, because if you assume triangular, then the ranking is different. So it does matter what the input distribution is.
So then, does it make sense assigning a precise value to the sensitivity in the interval method, where the assumption is that you don't know the distribution with the variance? I mean, I guess you can bound the variance, presumably.
Yeah, actually, that's what some people do when they want to like do imprecise Sobel indices. They basically they use the 95% confidence interval or something like that, and then they came out with a interval in the first order and an interval in the total. But still, they're using the variance. In the case of the interval, I'm not sure how the input the index can be an interval. Because we are basically computing, we are basically measuring the area in red and the area in gray, and this will change. This will change if you assume a input distribution or another. That's why this variance is different. These indices are different. But in the case of intervals, I'm not sure. I don't think they change. For this specifics of intervals, you get this maximum and this minimum. It will change if you assume a different distribution, of course. But for intervals, I think this is constant.
I know it could, like, because if you were to assign the uniform distribution to x1 in that case, presumably the output would end up being some, it would presumably be contained within that interval output.
Yes, so I think if you want to solve this by assuming, for example, by sampling, if you want to solve this by sampling, this was solved with interval arithmetic. But if you want to solve it with sampling, what you do is you assume uniform distribution and then you sample. So I think
would you expect that to be contained within that interval output?
Yes.
If you were to sample?
Yes. If it will be contained, in fact, yes.
But it would have,
in the case of the uniform, I'm not sure about any other. The shape will be different if you assume different distributions. It would not have this kind of sinusoidal distribution or whatever you call it.
So the sensitivity would increase relative to that. But then, so then in that sense, is the interval-based bound? I guess I was going to say, like, is that a lower bound on the sensitivity? But in the triangular distribution and uniform, no, it doesn't seem to be. Yeah,
I think it's constant. Like, if you assume this range, if you assume this minus pi, and you have this function, you will always get the same maximum and minimum, unless you start assuming distribution functions.
Thanks. Does that answer your question, Alex?
Possibly. I think I'm just confusing myself, to be honest.
Okay, well, maybe we can revisit that. I just want to check. Does anyone else have any questions that they would like to ask?
But yeah, thank you very much, Enrique. Sorry.
Yeah, thanks, Alex, for the question. I'm sorry
Thank you,
I
Alex.
did not be more precise with my answer.
Well, that's in line with the presentation, so good job. Scott, would you like to ask a question?
Yeah, thanks. So as you maybe know, I hate these variance-based methods, not because they're not useful or even intuitive, but because they pretend they're the only sort of sensitivity measures. And so pursuing our drive to drive a stake through their heart, maybe there's this feature that we can't reproduce with intervals. Maybe we can. So what's the prospect of that? You said it was correlation that was the difficulty. What do you think the things are that those variance-based methods can do that we can't do in other ways?
Oh, okay. So at the moment, we can, with variance-based, we can measure combination effects with the total indices, and comparing the total indices and the first order indices, we can have a grasp of if there are some combination effects in the model. With the interval based, I don't know how to do that. I don't know if it's possible. So you could, for instance, if you want to diagnose the Ishigami function, you could run the interval sensitivity analysis. You could get this pinching information, which is very useful for uncertainty reduction. But you also may want to know if there are combination effects between the input parameters, which Sobel indices give you the answer.
Can't you compare the jointly pinched versus individually pinched? If that's what I'm not sure what you mean by combination effects, but maybe there's some artful way to pinch.
So combination effects is basically that there's some element in the function that contains both inputs,
Right.
like in this case here, x3 and x1. So there's a term in the function that depends on x3 and x1 at the same time.
Right.
That's what you get from the total indices while comparing first order and total indices with the Sobel. With interval, you don't get that information. And maybe if you want to make a decision, in this case it's very clear because you have to ignore x2, but maybe you want to take into account that there is some combination between x1 and x3. That's information. So you want to get as much information as possible from the model, and different methods will give you different answers. In this case, as I said, Sobel indices give you a grasp of the combination effects.
You would say that some artful pinching strategy that pinched them jointly or severally couldn't replicate that observation about their combination effects.
I don't know how to measure that with intervals at the moment.
Could you not achieve that by propagating like the Cartesian product of subintervals on each of x1, 2, and 3 through the function? So you end up like, if you did like -3, -2 in x1 propagated with -3, -2 in x2 and -3, -2 in x3, you get an output interval in you get the output width from that, and then you propagate each of those sets through so you get a higher dimensional space that you could interpret in the same way as that will envelope a certain proportion of the possible output space.
Yeah, perhaps it's possible. This is at very early stages of development, so maybe I can try that. Yeah, I haven't think about it, to be honest. So there's room for improvement. Well, all I'm saying here is not definitive at all. It's just very preliminary. Yeah.
All right, thank you. Do we have any last questions?
I just a short kind of like remark for Enrique. So Enrique, not sure it might be relevant to what you are doing at the moment, but in our recent NASA Challenge publication, we actually propose a adaptive pinching algorithm. It's not, I mean, it's not that complex. It's a very simple algorithm to kind of like adaptively, kind of like decide where is the, if you want, where would you like to pinch if you want to like, pinching up to a point. So maybe we can consider that in the analysis that you're doing. I mean, I'm not sure if it's going to be 100% relevant, but just take a look and see if it would apply.
Yeah, so the adaptive pinching, it's a kind of a strategy to overcome the problem of selecting the point to pinch. But here, basically, we take advantage of the information we already got from uncertainty quantification. Like maybe you are interested in performing uncertainty quantification using interval analysis. So you can reuse that data you've generated to measure not only the sensitivity indices, but also to measure the pinching.
Yeah.
I think if you want to have a more detailed, so if you want to focus on certain region of the input space, you can perform adaptive pinching because it will give you like more resolution around that region. So it's something that could be introduced here. For example, we can see that here. It should be, this interval here should go from 0 to 5. But because the interval arithmetic is an outer approximation, it gives you something slightly higher than 5.
Yeah.
Maybe if you want to refine that, can be seen here. If you want to refine that, maybe you can do this kind of adaptive pinching, and then you will get a more accurate interval here.
Yeah.
Yeah.
Nice one. Yeah. Thanks so much, Enrique, once again.
Thank you.
Any more questions?
Yeah.
Please go ahead.
Simple questions. If you scroll up for one slide, so the first question is if I understand you correctly, you're using low discrepancy sequences when you model uniform distributions. Is this right?
So to get this, so you're asking me about the sampling method that you use to get to. Okay, in the case of the uniform, fortunately, the Sobol indices for the uniform case can be, in the Ishigami, can be calculated analytically. So these numbers, they don't come from any sampling method because they were calculated analytically. In this case, I used a sampling method derived from Sobol sequences, which is it's a low discrepancy sampling method.
Yeah. And another question, just maybe it's too simple. Why is for the uniform distribution the second sensitivity index is higher than for interval-based method? I mean, maybe if you do the modeling in the right way, usually if you have a lot of points, uniform distribution should approach the interval approach. Or maybe I'm wrong, but I'm thinking why you got the second index for interval-based is lower than for the uniform.
Yeah, I understand. So they are measuring different things. So the uniform, the uniform is measuring the variance, so it takes into account the density of the data across in the domain. And the interval based is not measuring the variance. So I don't think there is a equivalence between the interval based and the Sobol indices at all. I need to think more about it, but yeah, I think they are simply measuring different things.
Okay.
I don't expect the indices to match at some point.
Mhm.
I'm not sure I'm answering the question.
Okay. Okay. And when you do your calculations, do you handle somehow repeated variables in your Michigan function? Because if you scroll up to the previous slide, you got this x1 in the first term, and you also got x1 in the last term. Just when you put intervals into this function, you can have the dependency problem.
Yeah. Yeah, that's I think that's the reason this is not, it doesn't go exactly to 0 to 5.
Mhm.
I know about the dependency problem in interval arithmetic. There are some preliminary papers trying to solve some issues in the case of two variables.
Mhm.
We haven't used any of that here,
Mhm.
but it is true that if you have like a bigger model or more complex model, then the interval arithmetic.
Yeah, sure. Yeah, this model is a toy example, and I think it will be easy to remove the dependency by several methods.
But you could use sampling methods, which doesn't suffer of that problem, I think. So this, I just solved this using interval arithmetic, but it can be done with sampling methods as well.
Okay. Thank you.
Thanks for the question.
Okay. Do we have any more questions from the audience?
Just one quick on.
Go ahead,
Attack
Alex.
on that. Could you not just factor out the sine x1 quite easily and see if the repeated variable is what is affecting the output?
Yeah, I guess.
It'd just be a quick way to see if that is what's driving the difference that's seen on the output.
Maybe I can do that. I didn't think about it, to be honest.
Okay, any more questions from the audience at all? And if not, then let's thank Enrique again. It was a pleasure to have you. Quite a lively discussion as well, so that's always positive. Yeah, thank you very much. That was wonderful.
Yeah, thanks for the invitation.
Yeah, thank you.
And if you want to find your work, Enrique, do you put this online anywhere? Have you got any published works or ResearchGate profile? How can people keep up to date with your work?
So some of this has been submitted to, like it will hopefully will be presented at Israel in Dublin, but I haven't published anything about this yet. So yeah, I think Israel will be the first official place. Yeah.
Okay, fantastic. Well, good luck and thanks. Yeah, keep in touch and see you all very soon.
Thank you.
Have a lovely day, everyone.
You too.
Thank you so much.
There you go.